Okay, let's continue with our molecular orbital theory. In the last class, we constructed the molecular orbital diagram with the help of the symmetry adapted linear combination of atomic orbitals method. So today I would like to do a somewhat more complex example, which is the molecular diagram of ammonia, NH3. So we can go through the same procedures as we have done for the water molecule. So the first step is always to determine the point group. The point group of the ammonia molecule is C3V. So this is our first step we have now accomplished. We can now go to the second step, which is the determination of a suitable coordinate system. And one sensible coordinate system is shown here. So we have here the x-axis pointing to the right and the z-axis pointing to the top. And the ammonia molecule is oriented so that one of the three NH bonds is in the xz plane, okay? And a z-axis stands perpendicular to the base of the pyramid, which is made here from these three hydrogen atoms. Okay, so this is our second step. Next, we need to decide which are our central atom orbitals and which are our ligand orbitals. So our central atom would naturally be the nitrogen, and our ligand atoms would naturally be the hydrogens. So what would be the valence orbitals of the hydrogen? Well, again, that would be just the 1s orbitals. So we would have overall three 1s orbitals, and they would be combined to form three ligand group orbitals. Okay. So again, the number of the ligand group orbitals is equal to the number of atomic orbitals. So in the next step, we would then need to determine the symmetry types of our ligand group orbitals. And again, we can do this using the orbital swapping method that will help us to determine the reducible representation, from which we can then determine the irreducible representations. So we have to go through the symmetry operations step by step. In this case, we have the identity, we have the C3 symmetry operations, and we have the sigma V symmetry operations. For each of these, we have to determine whether the orbitals swap their positions or not. So orbitals that do swap their position, they get a character 0. Orbitals that do not swap their position, they get a character of 1. And we then need to add up the characters in order to determine the character in the reducible representation. So let us start with the identity, E. As you know, the identity never does anything. So all of the orbitals remain in their positions. So therefore, all of them get the character +1. So we add up these characters, and that gives overall a character 3. 1 + 1 + 1, well, that gives just 3. So that determines the first character in the reducible representation. So next, we go to the C3 symmetry operations, and we could either pick the C31 or the C32 symmetry operation. Wouldn't matter. We can just pick the C31 symmetry operation and ask ourselves, well, do the orbitals change their positions or do they remain at their positions? The answer is again pretty simple. The C3 axis would stand perpendicular to the basis of the NH3 molecule, to the base of the trigonal pyramid, and therefore we would rotate around all the three hydrogen atoms and the 1s orbitals with them. So if we rotate 120 degrees counterclockwise, we would move orbital 1 into position of orbital 2, orbital 2 in position of orbital 3, and orbital 3 in the position of orbital 1. So for that reason, none of the orbitals would remain in their place, so all of them would get the character of 0. So 0 plus 0 plus 0, that is 0, which determines the second character in our reducible representation. So last but not least, we have to look at the sigma v mirror planes. So again, we can choose each of the, or any of the sigma v mirror planes. So for instance, we can choose the sigma v mirror plane that stands here. It would actually go through this hydrogen atom, but not through the other two hydrogen atoms. And because of that, only the atoms number 2 and number 3, they're getting swapped up. But as you can see, the atom number 1 and also the associated orbital, 1s orbital, stays at its position. Therefore, in this case, this orbital here gets a character of 1, and the other two orbitals, they both get a character of 0. Okay, so now that gives overall 0 plus 0 plus 1, and that gives 1. So now we have found all the characters in our reducible representation. Our next step is then to determine, well, what are the characters of the irreducible representations that make up the reducible representation. Again, we can use the reduction formula in order to do this. So we can go through the irreducible representation step by step and apply the reduction formula to each of them. That will give us the number of irreducible representations of a given type. So you see here again the character table of the point group C3V. You see that in this case, there are 3 different irreducible representations to consider. The first one has the symmetry type A1, the second one has the symmetry type A2, and the last one has the symmetry type E. So we can, for instance, start with the symmetry type A1 and ask, well, what's the number of the irreducible representations of that symmetry type? Well, that will be 1 over the order of the point group. Now, the order of the point group is in this case 6. Why is it 6? It is 6 because we have 6 symmetry operations to consider. That's here the identity. That is here the 2C3 symmetry operations. And that is here the 3 sigma V symmetry operations. So it's 1 over 6 times this product here for all the symmetry operations. Okay, so we can start with the symmetry operation E. So the number of operations in the class would be 1, because we have only one identity operation. We need to multiply that one with the character of the reducible representation. Now, what was the character of the reducible representation? That was, and we can look this up here, 3. Okay. So we have 1 times 3, and that we need to multiply with the character of the irreducible representation. So what is this? Well, that's the character in the row for the irreducible representation A1 underneath of sigma V, and that is 1. So overall we have the product 1 times 3 times 1. So now we have to add to this term the term for the next symmetry operation, and that's the C3 symmetry operations. So we have now 2 to consider. So what is the number of operations in the class now? So in this case, it is now 2, because we have 2 C3 symmetry operations to consider. That's the C31 and the C32. So we have therefore a character 2 that we now have to multiply with the character of the reducible representation. So we can look this up, and we saw that the character was 0. Therefore, we have 2 times 0. What is the character of the irreducible representation? It is 1. Why is it 1? Because the character underneath C3 in the row for the irreducible representation A1 is 1. Okay, last but not least, we need to determine the character for the sigma V symmetry operations as well. So what is in this case the number of operations in the class? You see that in this case we have 3 operations in the class, okay, because we have 3 sigma V mirror planes. So the character is 3. We have to multiply this with the character of the reducible representation. Remember, we have determined previously that the character in the reducible representation for sigma V is 1. So 3 times 1, and we have to multiply this now with the character of the irreducible representation. And that character is 1 because the character in the irreducible representation A1 underneath sigma V is 1. Okay, so now what does that give? Well, this is 1/6 times 6 plus 0 plus, 1/6 times 3, 1 times 3 plus 1 is 3, plus 0, because 2 times 0 plus 1 is 0, plus 3 is equal to 1. So this here, that gives 6, and 6 over 6, well, that gives 1. So now we have found the symmetry type for the first of the 3 ligand group orbitals that we were looking for, and that symmetry type is A1. So now we need to do the analogous calculation also for the symmetry types A2 and the symmetry type E. Now the result for the symmetry type A2 would be 0, and the result for the symmetry type A1 would be 1. So I have not exactly calculated here the number of the irreducible representations with the sim type A2, but only the number of symmetry types, number of irreducible representations of the type E. So this is in this case 1/6, because that's again 1 of the order of the pointer, times 1 times 3 times 2. Why is that so? Because the number of operations in the class underneath E is 1. So the number of the character for the reducible representation is again 3. And the character of the irreducible representation in this case is 2. Okay, so this is this 2 here in the row for the symmetry type E underneath the character, underneath the symbol for the symmetry operation E. Okay, so we have to add this term, so this is 2 times 0 times minus 1. I mean, briefly think about why is it 2 times 0 times minus 1. So again, we have the number of operations in the class to consider. So that is, in this case, again, 2, because we have 2 C3 symmetry operations. So we have to multiply this now by 0, because that's, again, the character of the reducible representation, which was 0 for the C3 symmetry operations, because all 3 orbitals are getting rotated. And we have to multiply this by minus 1. That's the character of the irreducible representation. And that would be this minus 1 here. Okay, last but not least, we need the character for the sigma V operations also. So now the number of operations in the class is again 3, because we have 3 sigma V operations. So secondly, the character of the reducible representation is 1. That is because 2 orbitals get swapped and 1 stays. And the character of the irreducible representation is in this case 0. So this is this 0 here. Yeah. So now you see that this gives 1/6 times 6 plus 0 plus 0, and that's 6/6, which is again 1. So now at first glance, it seems that we have one ligand group orbital with the symmetry type E. But in fact, and that's very important to realize, we have two. And that is because of the double degenerate character of the symmetry type E. Remember, E means double degeneracy. There are two coordinates that are dependent on each other. In point of C3V, it's actually the X and the Y coordinate. And because of that, our result means that we have double the number of ligand group orbitals, not just one, but actually two. And that means now that we have found the symmetry types of all our three ligand group orbitals. Okay, one has the symmetry type A1, and the other two have the symmetry type E. That also gives us the information that we have two ligand group orbitals which are double degenerate. And that is very helpful, as we will see in a moment when we construct the molecular orbital diagram, because we know when two orbitals are double degenerate, they are not degenerate in terms of symmetry, but also in terms of energy. Okay? We'll apply this knowledge in a moment. All right, so then we need to look at the symmetry types of the central atom orbits. Again, this is a pretty easy job because we only need to look into the character table and see where the respective letters appear. So first of all, we know again that the 2s orbital of the nitrogen has A1 symmetry because s orbitals always have the totally symmetric symmetry type, which is always the first one in the character table, where all characters are +1. So therefore we know the 2s orbital has the symmetry type A1. Then what about the 2p orbitals, which are also valence orbitals? So now the 2px and the 2py, they have E-type symmetry, because you see they're in the row for the symmetry type E. You see also they are in parentheses. Okay, and that again tells you that these two orbitals are double degenerate in the point group C3V. And last but not least, we have the 2pz orbital. You see the letter Z here in the row for the irreducible representation A1, and that just means that our 2pz orbital has that respective symmetry type. Okay, now we have basically all the knowledge in order to construct our molecular orbitals. Let's first determine what orbitals we can combine and what symmetry type they would have. So we can again go through the symmetry types and determine, well, are there partners that can be combined to form molecular orbitals? If an orbital does not have a partner with the same symmetry type, then that again means that the respective orbital is non-bonded. All right, so now when we look at the symmetry type A1, then we notice that the 2s and the 2pz orbital has that symmetry type. We also have determined that one of the three ligand group orbitals has that symmetry type. So how many molecular orbitals of the symmetry type A1 would we expect? Well, that's the same as the number of orbitals we have started with, and that means that we will get 3 molecular orbitals of A1 symmetry type. So what about the symmetry type A2? So neither a central atom nor a ligand group orbital has that symmetry type. For that reason, we will not have any molecular orbitals of that symmetry type. And last but not least, we have to look at symmetry type E. We have determined that the 2px and the 2py orbitals have that symmetry type. And 2 ligand group orbitals also have that symmetry type. So therefore, we combine overall 4 molecular orbitals, and that means that we must get 4 molecular orbitals, symmetry type E. Now, because of the degeneracy, we know that we will get two bonding molecular orbitals that are doubly degenerate and must have the same energy, and two anti-bonding molecular orbitals that also have the same energy. So this is what we can read from the double degeneracy of these orbitals. We must now construct our molecular orbital diagram accordingly. Okay, so now let us just do this. So again, the first step is to draw the energy axis. And then the second step is to draw the letters for the atom symbols. The central atom usually goes to the left by convention, and the ligand atoms, they go to the right. And in the following step, we can then indicate where the atomic orbitals are. So the nitrogen has the 2s orbital, which has the symmetry type A1. In addition, it has the 2p orbitals that have the symmetry types A1 and E respectively. We know that the 2p orbitals have a higher energy than the 2s orbitals, so we must write them accordingly into the molecular orbital diagram. So then, for the hydrogens, we know that we have 3 ligand group orbitals. One has the symmetry type A1, and 2 of them have the symmetry type E. The one that has the A1 symmetry has actually slightly lower energy than the 2 that are double degenerate, because the A1 one does not have a node, while the E ones actually do have a node. One could again show this. There are methods to show this. I omit that here because I think it would be more distracting than helpful. You could also again write all these 3 orbitals basically at the same energy level. That would not be a mistake, and you find this also often in the literature because the energy differences between these orbitals are generally quite small. Okay, then we have to again go through the symmetry types and now write the molecular orbitals of the respective symmetry types into the middle of the molecular orbital diagram. So for instance, we can start with the symmetry type A1. So how many molecular orbitals of the symmetry type A1 would we expect? Well, we previously determined that it has to be 3. When we have 3, we can approximate. Again, consider here that we write a qualitative molecular orbital diagram, that one orbital has low energy in its bonding, one orbital has high energy in its anti-bonding, and the third orbital is approximately non-bonding and has intermediate energy. Okay, so you have to write your orbitals now accordingly into the molecular orbital diagram and also label them properly. So the one with the lowest energy is labeled the 1A1, the one with the second highest energy is labeled 2A1, and the one with the third highest energy is labeled 3A1. All right, then you can again connect the molecular orbitals with the core atomic orbitals and ligand group orbitals to indicate from which atomic orbitals and ligand group orbitals we have constructed them from. So basically you have to connect them with all ligand group orbitals and all molecular, all atomic orbitals that also have the symmetry type A1. Okay, now we have completed our A1 type molecular orbitals. Now let us go to the E-type molecular orbitals. So you see that we have 4 on the left here and 4 on the right. So that means that we must produce 4 molecular orbitals. But like I said, 4 because of the double degeneracy, we must produce 2 bonding ones of lower energy that, however, have to have exactly the same energy. Okay, so you have to write them like this into the molecular orbital diagram. And the other 2 are anti-bonding and also have to have the same energy, but their energy is significantly higher. Okay, So again, the order of energies of all the molecular orbitals in the molecular diagram is not completely unambiguous. So for instance, we wouldn't know exactly for sure that these two here, these two interbonding ones of the E symmetry type would have a higher energy than the three A1. I just write them because like this, because I know it's correct, because there are quantitative molecular orbital diagrams also that can calculate the exact energy, but I wanted to point out to you that from just qualitative construction of molecular orbital diagrams, you would not know this, for sure. Okay, so again, we would connect the E-type molecular orbitals with E-type atomic orbitals and group orbitals. So now we are done with our E-type molecular orbitals, and we see that there are no other symmetry types to consider. So therefore next, fill in the electrons. So how many electrons does the nitrogen have? Well, the nitrogen has 5 valence electrons. So 2 of them would need to go into the 2s, and the remaining 3 of them would need to go into the 2p orbitals. So what about the hydrogens? Well, each hydrogen would carry 1 electron. So overall, we would have 3 electrons here. So if overall 5 plus 3 is 8 electrons, and these 8 electrons must now go into the 4 molecular orbitals of the lowest energy. So that would mean that we would have to fill the 1A1, we would have to fill the 1E1s. So then we have spent 6 electrons, and the last one would be the 2A1. So this would be our highest occupied molecular orbital, and the one above, the 3A1, would be our lowest unoccupied molecular orbital. Okay, so now we can again make a comparison between the molecular orbital picture of the covalent bonding and a simple valence bond picture. So I've written here the structural formula according to valence bond theory. And according to valence bond theory, I would say, well, we have 6 electrons that produce the 3 bonds between nitrogen and hydrogen. So can we find these 6 bonding electrons also in our molecular orbital diagram? And you see we can, because we have this bonding molecular orbital filled, and these 2 bonding molecular orbitals filled as well. But wherever you see that in the molecular orbital picture, you see more, you see that these 2 electrons have a lower energy than these 4, an information that you could not actually see here in the simple valence bond pictures, where all the electrons appear to be kind of equivalent. So now what about this electron lone pair? So this electron lone pair is naturally non-bonding, and we find that, well, our remaining 2 electrons are indeed in an approximately non-bonding molecular orbital. It's the 2A1 here. Okay. So again, the valence bond picture of the covalent bonding and molecular orbital picture of the covalent bonding nicely complement each other. The molecular orbital diagram gives you more information at the expense of more work to construct the molecular orbital diagram. All right. Then this is what I wanted to say for now about molecular orbital theory. We will revisit molecular orbital theory when we discuss covalent bonding and dative covalent bonding, particularly in coordination compounds. But before we revisit the molecular orbital theory in this form, I would like to discuss another important basic concept which is useful in coordination chemistry, and that is the Lewis acid and base concept. Now I just need to quickly go here, exit this here. This. This. So you're all probably familiar with the Lewis acid and base concept. The new information that I want to provide here is how the Lewis acid and base concept actually relates to molecular orbital theory and how you can understand it better, take into account molecular orbital theory. So before we go through that, let us briefly review the very basics of Lewis acid base theory. So that theory was developed by Gilbert Lewis, and according to Gilbert Lewis, an acid is an electron pair acceptor, and the base, Lewis base, is an electron pair donor. Okay, so how can we understand Lewis acid base reaction? Well, this would be a reaction in which the Lewis base donates an electron pair to the Lewis acid so that a covalent bond would be formed. And because in this case, both electrons come from one partner, this would be called a dative covalent bond, or also a coordinative covalent bond, as opposed to a regular covalent bond where basically one electron each would come from the two bonding partners involved. However, as I would like to point out, there's no fundamental difference between a dative covalent bond and a so-called regular covalent bond. It is mostly a matter of point of view on the respective covalent bond, whether you want to consider it as a regular covalent bond or as a dative covalent bond. Okay, so here's an example. So here we have BH3, so this is Lewis acid. So here we have NH3, which is a Lewis base. So the NH3 can donate its electron pair to that borane to make a covalent bond between boron and nitrogen. So this would be a dative covalent bond. We can indicate this by not writing a line, but actually an arrow that would point from the Lewis base to the Lewis acid to indicate that the electrons came from the Lewis base. So the reaction product is often called an adduct from the Lewis acid base reaction. So the Lewis acid base concept is a very general concept, a very powerful concept that includes also the Bronsted acid base concept, as well as the Arrhenius acid base concept. And here are just a very few examples. So for instance, when you react a proton with an OH minus anion, you can of course consider this a Bronsted acid base reaction, because one partner acts as the proton donor and the other partner acts as the proton acceptor. So in this case, the OH minus ion would be the proton acceptor, and the H plus would donate itself. So it would be the proton donor. However, it could also be seen as a Lewis acid base reaction. because we could say, well, the OH minus is the Lewis base and donates an electron lone pair here, and the proton accepts that electron lone pair to form a covalent bond between the Lewis acid and the Lewis base. Okay, and the reaction product then would be the water molecule. Okay, you see in this view, the water molecule would have one regular covalent bond, which is this OH bond, and a dative covalent bond, which is this bond. Okay, of course, there's no fundamental difference between the two bonds. Whether we see the bond as a dative bond or not only matters on our, only depends on our perspective on the bond. All right, so more reactions can be considered as acid-base reactions. So the formation of the coordination compounds can also be understood as Lewis acid-base reactions. For instance, if we have zinc 2+ ions reacting with, again, OH- ions, again, the OH- ions could be considered as the Lewis base, the zinc 2+ is a Lewis acid, so we would, the OH- anion would donate an electron pair to the zinc to make a covalent dative bond. Okay, so in this case, the zinc could actually react with up to 4 OH- anions to form a tetrahydroxyl zincate 2- anion. So last but not least, even ionic crystals could be considered as adducts formed through a Lewis acid-base reaction. In this case, the cation would be our Lewis acid, and our anion would be considered as a Lewis base. So this way, we could explain the reaction between calcium plus and 2 OH- to form calcium hydroxide, which would be an ionic crystal. So why is that view possible? Because again, we can say, well, our OH- ion has an electron lone pair that donates to the calcium 2+ to make a dative bond. So in this case, the dative bond would be a very polar dative bond, so that we could consider it an ionic dative bond, but still we could consider it as a dative bond. Remember, purely ionic crystals are actually not possible because energy difference between the respective orbitals is always finite, so therefore always some degree of covalency must be present in even the most ionic crystal. Okay, so now let us see what molecular orbital theory can say about Lewis acid and Lewis base and Lewis acid base reactions. So from the molecular orbital theory standpoint, what would be a typical Lewis base? So from the standpoint of molecular orbital theory, a typical Lewis base would be a molecule which has an approximately non-bonding highest occupied molecular orbital. So for instance, the ammonia molecule would be such a molecule which is constructed the molecular orbital diagram of the ammonia molecule. And we have determined that this 2a1 orbital is our highest occupied molecular orbital. And have also determined that it's approximately non-bonding, okay, because it's that intermediate energy A1 orbital. The low energy one would be the 1a1, and the high energy one would be the 3a1. So now, why is an approximately non-bonding highest occupied molecular orbital ideal for Lewis basicity? Okay, so now first of all, the orbital of course has to be filled, otherwise no electrons could be donated. And in addition to that, the orbital should not be too high in energy, nor should it be too low in energy, because if that orbital was too high in energy, yeah, And that would be the case if our highest occupied molecular orbital would be an interbonding molecular orbital. Then the electrons would likely be transferred completely to the Lewis acid. And then you would actually not form a covalent bond between the acid and base anymore. You would actually form an ionic bond, and you would actually have a redox reaction. Therefore, an interbonding HOMO is not ideal. Okay, so now what about a bonding HOMO? Also not ideal, because if these two electrons are so low in energy so that the HOMO is bonding, then there's little tendency for that molecule to donate these two electrons. So in this case, unlikely a reaction would occur. Okay, so the non-bonding situation is therefore the best situation. The energy of the electron lone pairs or electron pairs is neither too high nor is it too low. So now, what about Lewis acids? So from the standpoint of molecular orbital theory, an ideal Lewis acid is a molecule which has approximately non-bonding lowest unoccupied molecular orbitals. Okay, so again, the non-bonding character of the LUMOS maximize the probability that its energy is neither too high nor too low. So if it was too high and the LUMOS would be interbonding, the energy would be so high so that unlikely electrons would be donated in this energetically very high LUMO. So if that LUMO, however, was bonding, then likely its energy would be so low so that electrons from a partner to it would probably be completely transferred. And again, you would most likely get a redox reaction. Therefore, again, an approximately non-bonding character is ideal, because then the energy of the LUMO is neither too high nor is it too low. Okay, then let us go through a number of possibilities how Lewis acids can interact with Lewis bases from the standpoint of molecular orbital theory. So in the first case, let us assume we have a donor A and acceptor B, and the donor A has a HOMO in the LUMO, and of course the acceptor has a HOMO in the LUMO as well. So let us further assume that the HOMO of the donor and the LUMO of acceptor have exactly the same energy. So what could be said of the dative bond that forms between the two? Well, in this case, we would expect an ideally covalent bond with the electron pair being shared equally between the donor and acceptor. So we would have an ideally covalent dative bond in this case. So now we can say, well, let's make the energies of the orbitals different. So for instance, let us assume that the HOMO of donor A is now somewhat higher than the LUMO of acceptor B. So in this case, we would still be able to form a covalent bond, which would have dative character. However, now the bonding molecular orbital, which hosts the electrons, would be located primarily at the acceptor B. And that would mean that we would now have a polar covalent dative bond, which would be polarized toward the acceptor B. So we could take this another step further and make the HOMO of the donor A much higher in energy than the LUMO of acceptor B. Okay, so in this case, we could still construct a bonding molecular orbital, an anti-bonding molecular orbital. Again, the electrons would go from the donor into the bonding molecular orbital. But because the energy difference between donor and acceptor is now so large, these two electrons would now be located practically exclusively at the acceptor B. So for that reason, it would not be really adequate anymore to consider this reaction as a Lewis as a base reaction. Rather than that, we would say, well, we have now a redox reaction in which the donor A is getting oxidized and the acceptor B would be reduced, and we would form an ionic crystal. Okay, now we can also go into the other direction. We can say, well, let's make the LUMO of the acceptor B somewhat higher in energy than the HOMO of the donor A. So in this case, we can again form a bonding molecular orbital and an anti-bonding molecular orbital. So the two electrons coming from the donor would again go into the bonding molecular orbital. But now that bonding molecular orbital would be localized primarily at the donor A. So that means that we would have a polar, dative, covalent bond, which is now polarized toward the donor A. So now we could take this another step further and say, well, we further raise the energies of the donor B, so that now the LUMO of the donor is now significantly higher in energy than the HOMO of the acceptor. However, in this situation, you see that the LUMO of the acceptor becomes very similar in energy, or likely very similar in energy, to the HOMO of the donor B. So now these two have actually more similar energy than these two. Therefore, now the interaction will be primarily between these two. And that reverses the role of the two species A and B. Yeah. So now A will actually be the acceptor and B will be the donor. Okay, because we form a stronger covalent interaction between these two rather than these two. Okay, so if the energy of these two orbitals here is very similar, it would form again pretty much an ideal covalent bond. All right, then there's one more case to consider, and then we just complete this. We can raise the orbital energies of B even further. Now, even the HOMO of B is much higher in energy than the LUMO of A. So in this case, again, we would get actually energy transfer practice. So we would actually get a redox reaction, and the electrons would be transferred from B to A, and would form an ionic crystal, whereby, well, A would be the cation and B would be the anion. All right, let us stop at this point.